So continuing chapter 14, we're actually going to talk about probability today. Yesterday we just talked about the law of large numbers and the non-existent law of averages. Right? So we know that probabilities come from long-term relative frequencies, and that the law of averages, even though people say things like that all the time, is not actually valid. Okay? Chapter 14 probability stuff, again, is basic probability rules that you guys know. So this should not be the end of the world. Okay? So when you are modeling probability, all right, if they are made up of equally likely outcomes, which in this chapter we're going to have lots of things that are made up of equally likely outcomes. Cards, dice, that kind of thing. All right, M&M packages, whatever. We just count all the outcomes that the event contains, and the probability of the event is the number of outcomes in the event divided by the total number of possible outcomes. You guys know this. This has been since you learned probability in middle school. Okay? Again, I want to make sure that you are using notation. On a lot of these questions today, it is really easy just to calculate the answer and be done. I get it. But if you're faced with a free response question, which there's always some sort of probability type free response question, you need to have the notation because it's a free response question. So I'm going to make you, on your homework, write out the notation. So the probability of whatever event, so P of whatever, equals. That way you're using it, and that way you don't forget to use it later on. Okay? Just to be aware that also there's such thing as a personal probability. And that's when you're talking about things that you're like predicting in your life, whatever. We use it kind of like in the English language, like I think I've got like a 50% chance of getting this quiz done or whatever. Those types of things are personal estimations. Make sure you're not using personal estimations in anything that we're doing, or at least making a distinction between personal probabilities from everything else that we're doing. Okay? That's just a note. Make sure you're not thinking about that as an actual probability. In this textbook, not so much for this chapter, but for all the rest of the stuff on probability, you need to make a picture if at all possible. Again, not necessarily so much of this chapter. We can do this chapter without pictures most of the time. But in other chapters, you want to make a picture. That way you know what events overlap, what happens. In chapter 15, we're going to be using tree diagrams and Venn diagrams and all sorts of things. So if it's a complex question, make a picture to make sure that you kind of have a visual. This is not the first time our book has said to make a picture. They said that again at the beginning of the book. So again, making a picture might be a valid way of kind of getting started on some things. All right. There are 5 formal probability rules or axioms in this chapter. You know, again, these are not new, but we'll go over them to make sure that you are thinking about them so we can do the assignment today. All right? The first one, if the probability is 0, that means it can never happen, whatever the event is. It literally can never happen if the probability is 0. The probability is 1, that means it always happens all the time. So we have the first rule as the probability has to be between 0 and 1. It can be equal to 0, it can be equal to 1, but it can't be negative, and it can't be 1.7. Again, you guys all know that. If you have multiple possible outcomes, the probability has to be distributed between those possible outcomes. So since the probability can never be greater than 1, all of the events have to add up to be a probability of 1. So all of the possible outcomes have to equal 1 when you add them all together. The set of outcomes that are not in a specific event is called the complement. Our book uses the event with a C, that's a complement. Other books use different things. But the probability of an event occurring is 1 minus the probability that it doesn't occur. So that might be helpful, some things today. Keep in mind that the event and its complement together make up the entire sample space. So this is a perfect picture of the complement. You have the possible outcome and then the outcome that's not happening in the gray area, so it makes up the entire sample space. There's nothing else going on. Mm-hmm. If you have two probabilities that are disjoint events, which means at no point do they overlap, you're in one group or the other. So pretty much or. You have the addition rule. So disjoint events, also known as mutually exclusive, you will see this on the AP exam all the time as mutually exclusive, yet our book just calls them disjoint and never uses the term mutually exclusive. So you might want to make a note that disjoint is mutually exclusive, just so that you know the vocabulary. Again, disjoint events have no outcomes in common. There's no overlap. If you have a Venn diagram, there's one down here. You have the two events completely separate. The addition rule says that if you have two disjoint events, that the probability that one or the other occurs is the sum of the probabilities of the two events. I don't know if, I am assuming Mr. Scott used this notation, but if he hasn't, set notation, this U means union, which means or. We'll also have an upside down U that means intersection, and that means and then a little bit. But you should be familiar with that notation. Again, the events have to be disjoint to just add them together like this. The book gives an example that if you know the probability of owning an MP3 player and you know the probability of owning a TV or a computer, those are not disjoint events. You can own an MP3 player and a TV and a computer. Okay? So you would not be able to just add probabilities that way. When you start doing those things, you generally end up getting probabilities over 1. So a few things again, make sure you know disjoint means mutually exclusive. Make sure you know the notation, the union and intersection and in ors. And then make sure, of course, the addition rule, you can add two together if they're disjoint. Everyone go with that rule. Disjoint would be like if you're picking out M&Ms and you're trying to figure out the probability. You know the probability of being green, the probability of being blue. And what's probably being a green or a blue? The M&M can never be green and blue. So they're disjoint. All right, last rule is the multiplication rule. The multiplication rule relies on the fact that events are independent. Independence in this case means that the outcome of one event doesn't influence the outcome of the other. So in this example, they're talking about flying from Atlanta to Houston every Monday morning. The airline's website reports that the flight is on time 85% of the time. What's the chance that it'll be on time 2 weeks in a row? Well, you'd be able to multiply that probability by itself. It's two separate events, two independent events. So the multiplication rule says for two independent events, The probability that both A and B occurs, the product of the probabilities. So here we have our notation for an intersection, which again means and. Again, they have to be independent. We'll talk more about independence and disjoint tomorrow. Make sure you know the difference. Those are the 5 probability rules that we're focusing on in this chapter. Again, those are ones you guys know. Those are ones that aren't super complex. The probability questions where there's a lot more going on are going to happen in chapter 15. Okay? So I've got just a lot of examples, and we're going to go through all of them. That way everyone's on the same page and no one's confused, and I've shown you a variety of different types of things. Okay? First, we're going to do some examples from your textbook in the actual chapter. So we open the chapter by looking at the traffic light at the corner of College and Main, observing that when we arrive at the intersection, the light is green about 35% of the time. So if the probability the light is green is 0.35, what's the probability the light isn't green when you get to College and Main? So how would you find that out? Subtract it from 1. Again, we're going to make sure you're using the notation. So probably that it's not green. This is on page 330. That's 1 minus 0.35, which is 0.65. And make sure you're using the notation. The next one, when you get to the light at College and Main, it's either red, green, or yellow. Again, the probability that it's green is still 0.35. Suppose we find out that the probability of yellow is about 0.04. What's the probability the light is red? So how are we going to figure that out? What's the first thing we need to do? Right, we need to add green and yellow. So the probability that the light is green or yellow is what? 0.35 plus 0.04, which is 0.39. So then how do I find the probability that it's red? These are basic probability rules. These aren't anything crazy complex. Questions on that one? All right, we've determined that the probability that we encounter a green light at the corner of College Main is 0.35, a yellow light is 0.04, and a red light is 0.61. Let's think about your morning commute in the week ahead. What's the probability you find the light red on both Monday and Tuesday? So if we're talking about Monday and Tuesday, are those 2 trips independent events? Yes, one doesn't influence the other, so you can use the multiplication rule. So the probability that the light is red on, that's an M, okay, on Monday and Tuesday is going to be what, 0.61 times 0.61? Because they're independent, one after the other. You're adding if it's going to be something or the other. Here we have and. So when you have and, in general, you're going to multiply. So that's a good point. Or, add, and multiply. Okay? So what's 0.61 times 0.61? Does that make sense while we're multiplying it? Yes. Okay. What's the probability you don't encounter a red light until Wednesday? So that means you have the probability, if you want to think about it this way, that it's not red on Monday, right? And not red on Tuesday, but then it's red on Wednesday. Does that make sense? I'm just putting that into notation there. All right. So what was the probability that was not red? Don't we have that somewhere else? 0.39. Okay. So that would be, since we're doing ands, we're going to be multiplying. So 0.39 times 0.39 times the probability that it is red is 0.61. So that probability ends up being 0.092781. Also, if you get confused about adding and multiplying, on both of these questions, if you started adding, you're going to get probabilities over 1. So then you're going to have an obvious problem. In statistics, we generally leave them as decimals. So I know that generally in other classes use percentages. We normally leave it as decimals because in later chapters we're going to be using these probabilities to do other things. So we just generally leave them as decimals. Good question. So far, so good? All right, on the last one. Note that the phrase "at least" is often a tip-off to think about the complement. Something that happens at least once does happen, and happening at least once is the complement of not happening at all. And that's easier to find. So if they're asking you questions saying at least once, let me think of it once or twice or 3 times or 4 times or 5 times, in this case with this 5-day commute, right? Well, it's easier to find that it's not ever happening and subtract from 1 than to find all of those individually and multiply everything, okay? So what's the probability that you'll have to stop at least once during the week? So again, I could either calculate the probability of getting a red light once, getting a red light twice, getting a red light 3 times, 4 times, 5 times, and put it all together, or it would be easier if we just did 1 minus. So we want to do 1 minus the probability of no red lights. Because that means that we are never stopping, right? And 1 minus that would mean that we got the probability that we got stopped. Does that reasoning make sense? Okay. So this is a 5-day work week commute. So no red lights is the probability of not being red 5 times in a row, right? So technically the book would say not red and not red, etc., 5 times. That helps you figure out what numbers you're supposed to be using. So what's the probability of it not being red? 0.39, right? That was probably being green or yellow. So you're going to do that multiplied by itself 5 times. You're totally right to the 5th power, and that's totally fine. According to the textbook, that ends up being 0.009. So the 0.009 is the probability that you got a green or a yellow every day. So 1 minus that says is the probability of getting a red at some point, which is what it's saying, at least once. So you end up getting 0.991. Out of all of the questions in the chapter, these questions are going to be the hardest ones you have to answer, I promise. All right. Questions on that example. Okay. Can we do another one? I've got a lot to do. I just want to make sure we're all on the same page. Again, another example straight from your textbook. The 5 rules we've seen can be used in a number of different combinations to answer a surprising number of questions. So in 2001, Master Foods, the manufacturers of M&M's milk chocolate candies, decided to add another color to the standard color lineup of brown, yellow, red, orange, blue, and green. To decide which color to add, they surveyed people in nearly every country of the world and asked them to vote among purple, pink, and teal. The global winner was purple. In the United States, 42% of those who voted said purple, 37% said teal, and only 19% said pink. But in Japan, the percentages were 38% pink, 36% teal, and only 16% purple. And we're going to use Japan's percentages to ask some questions. So we're looking just at these values. This is on page 333. So see, 3 separate questions. We'll separate them all. You have to look at them all at the top. So question 1, what's the probability that a Japanese M&M survey respondent selected at random preferred either pink or teal? So here we got the probability of pink or teal. So if we have or, what rule are we going to use? We're going to add. So what was the probability of pink? 38, so 0.38. And teal was 36, right? Okay. So that ends up being 0.74, 74%. Questions about that? No. Again, in stats, we only use decimals. After this chapter, we're going to be using probabilities a lot, and we generally need to be in decimal form. You're right. You're right. It does equal 90. I'm going to go with that's a typo in the book. No, actually, the book goes back and we have, it says, like the very first, I skipped that part of the question because it wasn't relevant to this question, but it says it does add up to 90, so you would assume there would be 10% that had no preference. I just didn't give that to you in the prompt. So that didn't help us answer this question, so I just didn't put it on here. That's a good catch, though. That's the type of thing you're thinking about. Other questions on question 1? Question 2, if we pick 2 respondents at random, what's the probability that they both said purple? So what rule are we using here? And. So purple and purple. So that was the, what, 16%? Right? So we're multiplying, and you get a probability of 0.0256. Questions about that one? Okay, the last one here. If we pick 3 respondents at random, what's the probability that at least one preferred purple? So again, if you have at least one preferred purple, that means you'd have to do the probability of 1 picking purple, 2 picking purple, and 3 picking purple. Or you could just do 1 minus the probability that none picked purple. Just less to do, in my opinion. All right, so what's the probability of not purple? It would have to be, well, pink and teal was 74, and then going back to what Brandon said about how it doesn't add up to 100, right? It'd be 90, so it adds in that 10% of no preference people. So 84% would have not picked purple. So we're talking about 3 respondents, right? So 0.84 3 times. That's 0.5927. And so you get 0.4073. Questions about that one? Okay, I've got got a few more. We might not do all of them, but I've got a few more, and then I'll give you the assignment. The first one for you. Yeah. It was talking about 3 respondents, so I could have just written out respondent 1 didn't pick purple, respondent 2 didn't pick purple, and respondent 3 didn't pick purple, but I got lazy. So I put a third power. Other questions before we move on? All right. The plastic arrow on a spinner for a child's game stops rotating to point at a color that will determine what happens next. Which of the following probability assignments are possible? So all of these are separate assignments. You're just going to tell me which ones are actual probability assignments. So you need to make sure what's happening between these probabilities. Like, which one can you just look at it immediately and say that is not one? E. E is not a probability assignment because there's a 1.2 and there's a negative, and both of those are not allowed in general ever. So E would not be a possible probability assignment. Now the other ones look okay, so you need to go back and do some adding, right? Does A add up to 1? Yes. Does B add up to 1? C does not, right? Because you have 90 just here. So C does not work. And then D does add up to 1. I don't know how that would be a very good children's game when it's all the same thing, but it adds up to 1. All right. Questions about that? Does that make sense? The next few are just talking about thinking there's some reasoning, so we're not actually doing anything. Suppose that 46% of families living in a certain county own a car and 18% own an SUV. The addition rule might suggest then that 64% of families own either a car or an SUV. What's wrong with that reasoning? Right, these are not mutually exclusive or disjoint. You could own a car and an SUV, right? So then you can't add them. We'll talk about things like that in chapter 15. Number 15. Traffic checks on a certain section of highway suggest that 60% of drivers are speeding there. Since 0.6 times 0.6 is 0.36, the multiplication rule might suggest that there's a 36% chance that 2 vehicles in a row are both speeding. What's wrong with that reasoning? Right, why are these not independent? Right, think about your driving habits, and if you're on the highway, right, so you're out on the Purchase Parkway or something, all right? If the person in front of you is speeding, you're probably going to be speeding as well, right? The person in front of you being slow, until you can pass them, you're going to be being slow as well. So those aren't independent events. One car is influencing the other, all right? So those are not independent. Questions on that? That one's kind of a little harder to understand, I think, but we start thinking about driving, flow of traffic, those type of things. All right, these last 3 all go together and I'll be done. A consumer organization estimates that over a 1-year period, 17% of cars will need to be repaired once, 7% will need repairs twice, and 4% will require 3 or more repairs. What is the probability that a car chosen at random will need? And it gives us some different questions. So, the probability that the car is going to need no repairs. How do I find that? Right. So 1 minus the probability of repairs in general, right? So that's 1 minus 0.17 plus 0.07 plus 0.04. Does that one make sense? Questions on it? On B, probability that the car chosen at random will need no more than 1 repair. So that means the car would need either what two things out of our choices? No repairs or one repair. So then we can add those two together because those are disjoint. The car's not going to need no repairs and one repair. So that's just what, 0.72 plus 0.17. Yes, you could. Mm-hmm. And then the last one's the probability of some repairs. So what's the probability of some repairs mean? Yeah, it could be one repair and two repairs and three or more, right? So that's what was in the parentheses on part A, which should have been 0.28. So far, so good? Those are ors. All right, and 21. Consider again the auto repair rates described in exercise 19. If you own two cars, so now we have two different cars. So now we're going to be able to use the addition rule. If you have two separate cars, can you use the addition rule in these problems? Probably not, right? You're going to have multiplication for both of these independent vehicles. So what's the probability that neither will need repair? Well, that means you have probability of no repairs for car 1 and no repairs for car number 2. So and means we're going to multiply. So no repairs was 0.72 from above. And that's 0.5184. On B, we have probability that both will need repair. So that's the probability of some repairs if you're looking at 19 for car 1 and some repairs for car number 2. So that probability was 0.28. That's 0.0784. And the last one, at least one car will need repair. So that is 1 minus the probability that they both have no repairs. Didn't we already find that probability? The second half of this? This part was part A, right? Probably that both needed no repair. So that's just 1 minus part A, 0.5184. That's 0.4816. And then 23 is not doing anything, we're just thinking again. You'll use the multiplication rule to calculate repair probabilities for your cars in exercise 21. What must be true about your cars in order to make that approach valid? In order to use the multiplication rule, what has to happen? Almost. Yes. So addition rule, they have to be mutually exclusive. Multiplication rule, they have to be independent. So cars must be independent. Do you think this assumption is reasonable and explain? Some things you might want to think about. How do the car owners take care of their cars? If they just ignore all the stuff on their dashboard at all times, right? Then, or they ignore, taking care of regular maintenance. maybe they aren't mutually or aren't independent, because then the same owner, same problems. And also, how old are these cars? We have two 15-year-old cars. That's going to make a difference, right? So those are some things that might make them where the events would not be independent. But it's just some things to consider.